So here is the Mathcad for the steel portal frame design check, and we're checking for bending, shear and axial load of our frame members. So we begin with a summary of the analysis results we got from multi-frame. So for each of the load cases here, we've got the 1.2 dead plus a 1.5 live, and following a P delta analysis. And our maximum moments, shears and axial forces are given here. And we repeat the exercise for our wind with dead load down, and then we have wind up with our minimal dead load. And these are the moments, shears and axial forces for that. So that's a summary of the loading that you're putting on the frame. Okay, so we start with the rafter check. So our rafter span is 20.7 meters long. And we're looking at the loading going on that rafter, and we picked out the numbers from above to give us our maximum axial load, shear and moment applied. So we put in some basic information for the rafter. We have a Young's modulus E as 200, shear modulus G is 80, and then our strengths, yield and ultimate is 304.30. Our strength reduction factor for our members is 0.9, and that's taken from the table. So we pull out the section properties from the rafter, and Steel and Tube provide full data tables from this. You can just copy them over. Similarly for all the I values and Z values and S values. So the elastic section modulus and the plastic section modulus you're looking at, and in particular the radius of gyration about the major and minor axes. The Steel and Tube catalogue also tells you what the form factor is, so you don't actually have to work it out. So moving down, we pull out our slenderness parameters. And this is looking at clause 5.2.2.1 in the code. And then we compare it with the limits given in table 5.2. And for our section classification has come out as compact. For anybody who's used to Eurocodes, this is slightly different from our Eurocode classification, where we had a much larger range of section classifications. So we begin with a basic bending check for the rafter, and we look at the section modulus, and we look at the section moment capacity elastic in this case, so 444 kilonewton meters. So if it's fully restrained, the section capacity is going to be 444 for that beam. And putting on a strength reduction factor, we get a capacity of 400 kilonewton meters. We can do the same exercise for a minor axis and come out with a bending capacity about the minor axis of 68. So we can compare the section capacity against the applied moment, and we're still good. We're 91% now, so we're quite close to the limit on that. If we'd failed on this, we need to start again. Basically, our section isn't big enough. And that'll save you the time for the rest of this, because the rest of it gets a lot more complicated. So we're looking at buckling, and it's buckling about the minor axis. So your major axis capacity for a rafter depends upon the buckling about the minor axis, and the minor axis is restrained along the length of your rafter. So you've got a 20-meter long rafter, but you want to divide it up. Conveniently, we have purlins at regular intervals, and the little trick is to double or halve the space between the purlins at the eaves and the apex, and that halves the effective length that's unrestrained. So we've now got a length between the restraints, so we've got 1150 millimeters between our restraints. We look at the moments at the ends of that section, which is 362 at one end, 255 at the other end, and this gives us a end moment ratio, or a beta M, as 0.7. We can plug that 0.7 value into the equation given in table 5.6.1 for our style of loading, and that points out a alpha M of 1.16. we can just check that are we restrained or unrestrained. Now, given those values, it turns out that this section is actually restrained anyway. So buckling shouldn't be a problem. I've conservatively put in the KL as 1.4, although it could be 1, as I discussed earlier. So the effective length of my segment is 1.61. A reference buckling moment taken from the equation 5.6.1.1, and the sharp-eyed would notice that this bit is the Euler buckling value for axial compression on a strut. Then we add the torsional buckling value, and we derive our slenderness reduction factor based upon that reference moment, and we compare it to the capacity, and that spits out an alpha S value of 0.938 with a nominal moment capacity coming out as 482. Now, that's actually bigger than the section capacity. And if you remember Euler buckling, you'll notice that the strut curve actually goes up way past the yield capacity and never actually reaches the y-axis of that Euler buckling diagram. So we take the minimum value for the buckling moment or the section capacity moment. And so we're looking at a design bending capacity of 400. Okay, that's relatively simple, honest. There is an alternative method given in the code. It allows you to derive the alpha m from this equation here. But you need to know what the moments are along your segments. So remember, your segment is the length of your rafter between restraints. And so if you zoom in on your bending moment diagram, you get the moments on either end, and then you want the moments in between. So your M2 is the bending moment at the quarter point, M4 is at 3/4, and M3 is the one in the middle. Now I've cheated a little here because I've assumed I've got a linear distribution of bending moment between the two ends. In reality, it won't be, it'll be slightly different. But for the sake of this exercise, we can use a linear distribution. So our moment modification factor alpha m spits out through this equation as a 1.149. And our alpha s, again from above, and then our moment capacity pops out as 478. It's slightly different from above, but quite close to it. So the two methods give you similar results, but not exactly the same. But again, in this case, our section capacity dominates. Now, if that was the worst case, you could stop there for your bending and buckling capacity. However, as we've said, for maximum efficiency, you halve the spacing between the purlins at the eaves and the apex, because that's where the maximum moment is. So we need to look at the next section. And we pick out another section, and the length between the restraints is now 2.3 meters. And we go through the same routine again, find our reference moment, and we actually I've actually put these in from the bending moment diagram given by multi-frame analysis. And that pops out our maximum moment. So the MN is the maximum moment. It's not the end moment. It's the maximum moment in that section. And that gives you an alpha M modification factor as 0.995. And that spits out your design bending capacity of 285. Now we're comparing it with the maximum moment applied. So the maximum moment in this section is less than the previous section. So therefore our maximum moment is smaller than our capacity, which is okay. Right, so that was bending and buckling. Now we need to check shear. The first thing you need to do is check whether your web is stocky or slender. And we use that equation from clause 5.11.2.1. and we find our gross sectional area of the web, multiply by the yield, and with a 0.6 factor applied. So our nominal shear capacity is 694. Put in a strength reduction factor, and we find that we're only 15% used. Okay, now that's straightforward shear capacity, but you might want to look at the shear buckling capacity. So slender webs, this isn't a slender web, but if you have a slender web, you need to check shear buckling of the web. So your alpha V, again, is coming from the code equation, and it comes out as 2.2. This, therefore, is bigger than your standard shear capacity, which means you take the minimum of the amplified or reduced shear capacity and the straightforward shear capacity you've worked out before. So we stick with our 694. So that was shear. Move on to the axial load check for the rafter. We've got our form factor, we've got our effective areas. We allow a little bit less sometimes for volts. And we look at the effective length. In this case, it's 3.22. And we've got our effective length for the major axis as 1.2. And we can derive the slenderness reduction factor to 140, and alpha A as 13, again from the clauses in the equation. Because it's an I-shaped section, alpha B is 0. Different sections will have different alpha B values, so you've got to look it up in the table. We get a lambda as 140, multiplying those together, and eta of 0.415, epsilon as 0.789, and finally an alpha C derived from all of that above as 0.3. So we've taken that 0.327 and multiply by a nominal capacity of the section itself. So we get quite a large figure of 775. And so our applied load in the rafter in axial compression isn't that great, so therefore our utilization is only 16.2%. Then we need to look at a combined check. And this is telling me that there's a little test as to whether axial load is significant. And so if you're at 5%, if you're less than 5% of your capacity, then axial load is insignificant. In our case, it's slightly above, so it's still significant. So we need to check the combined actions. So we reduce the nominal section capacity due to the presence of axial load, and we check it against the values given in the clause, 8.3.4, as a combined utilization ratio. And again, we've got an alternative design provision given in clause 8.3.4, and you can combine the two factors together with our reduced axial capacity and get our reduced moment capacity there. And we then derive this gamma factor, and our utilization factor comes out not just simply the applied load divided by the capacity, but we factor it by, in this case, 1.5. Happily, we're still under.